Hey, so this is a presentation for a paper submitted to CVPR 2020, and the name is Active Vision for Early Recognition in Human Actions. And it is being written with Bo Wong and his co-authors. And all the authors are affiliated with Stony Brook University. So here's the table of contents. Here's a list of contents that I'm going to cover in this presentation. First of all, I'm going to give you an overview of the whole thing. I will quickly summary the key ideas and the contributions made in this paper. And after that, I will explain the methodology in depth. I will describe in depth the models and formulations in this paper. And thirdly, I will go over the results. I will present them and compare them with the state of the art as of that time. And at the end, I have a conclusion part, which will point out the positive points in this paper, some things that have been ambiguous for myself, and some questions that need to be answered and are good potentials for extending this study. All right, as for the overview, I will first cover the terminology, then I will go to the motivations of this study. After that, I will describe the problem and introduce its notations, and at the end, I will present the data sets used in this study. All right. So the purpose of this study is to find a solution for early recognition of human actions. And its applications are actually numerous. They range from robotics to surveillance and healthcare. For instance, if you are trying to recognizing an elderly falling in the house, that domain is healthcare. And in case you are trying to control an intersection, that is for surveillance. And action recognition usually refers to a problem that, given a sequence of images, one wants to determine a category of actions performed. And multi-view recognition usually refers to any sort of recognition when the data has multiple viewpoints instead of only a single viewpoint. And early recognition refers to a situation that in which the recognition task needs to be performed using as limited time as possible. And active recognition refers to a system which selects its viewpoints dynamically. So it has this active part, it has this active module that interacts with the environment dynamically and controls the viewpoints. And this work is surprisingly in the intersection of all these areas. Right, the motivations behind this study, according to the authors, are fourfold. Previous studies only considered single view action recognition. Most of previous study, there has been some studies that consider multiple viewpoints, but they are using all the data possible, all the data in hand at the same time. They're not using it actively. So they are adding this multiple camera to solve that shortcoming. And previous works also, most of previous works studied this problem in an offline accurate recognition scheme, which is not sufficient, as I told you, in some application, such as detecting the fall of an elderly. You need to do that as soon as possible. So they are using an early recognition scheme here. Previous studies did not consider time and computation constraints, but the key idea and the key motivation behind this work is to reduce the amount of data that needs to be transferred after the model has been done processing it. So they are considering time delays and computational resources as well. Previous studies did not perform this task in an active paradigm, as I mentioned before, and they are using an active vision scheme here. Right. So this is the problem. So given K camera views, each having L frames per second, generally select the most appropriate frame at each time step while optimizing the recognition performance. data center is long, so the short version is you have multiple cameras and you have a couple of people performing an action, and you need to select the best viewpoint that you can have for determining the action at the end. For instance, in this picture, which is from the paper itself, camera one, the persons are occluded by a sofa and table. Camera two has this top view image. Camera three doesn't really cover the action here, and camera four seems to be the best one. And these people are, I guess, handshaking at some sort. And here is some of the notations used in this paper. So K stands for the number of cameras. L is the frame per second for all cameras, and belief state refers to a vector representing the state of the agent. And this belief state is given using MFRNNs, which we will cover later. And P, T, and pi. T are recognition probabilities and camera selection policy, respectively. And RT is a reward function, which is the negative cross entropy. We will cover that later too. And GT is the discounted reward summation, which is a standard thing in reinforcement learning problems. HT and I is the head and state of the ith MFRNNs, and a time step T, because they are recurrent neural networks, so they have this time step component in them. And XTI is the observation of the ith camera in time step T. And delta T and I is time spent from the last observation for the ith recurrent neural network. This thing will be made clear when we reach that state that we are covering the methodology. But as for the data set, this study is mainly using 3 different multi-view data sets. This first one is NTU or GBD. This data set is collected by 3 cameras capturing human actions from different views simultaneously. And they have 3 views and 60 action classes. And for these subjects are performing those action classes. And to test and to split the data set, they have considering splitting it under the subjects. So we have 20 subjects for training and 20 subjects for testing. And it contains RGB images and a skeleton of each person, which is 25 3D joint locations. And in this study, only the skeletons were used. And here's a video, is a sample video of the data set, and these men are handshaking, I guess. And the second data set they use is called IXPath. It has 11 action classes for camera views and RGB images, but it doesn't have the skeleton. So they are using this i3D model to extract features. Here's a sample action from the data set. I'm not sure what that action is, probably saluting someone. And the third data set is NV gesture, which has 25 classes, 2 viewpoints, and 5 modalities. And they used, again, i3D model for feature extraction here. They have 2 cameras, but they have 5 modalities. Modalities are RGB, image, optical flow, depth map, IR left and IR right. They also have the disparity map, but in the paper, they mentioned that using disparity map doesn't really help their model and their implementation, so they are ignoring it. So they have 5 modalities. All right, the second part is a methodology. So the way I will cover it, I will first explain what the belief state is and how the authors are dealing with the missing frames. And then I will cover the new structure of a novel recurrent neural network called missing frame RNN. And going through the end, I will cover how these outputs from all RNNs are integrated, and at the end, how the policy of camera selection is learned. So the belief state is some sort of vector that integrates observations over time to capture the dynamics of human action. And this is a pretty standard thing to do because actions are not, they have these dynamic components and they span over the time. So weekend neural networks is a good choice to go with. They model the belief state using multiple RNNs, one RNN for each viewpoint. For instance, for the first data set we had 3 viewpoints, so we have 3 RNN lines here, and x1 of 1 xt of I is denoted as the observation in this time step t, and for I camera. So this is the first observation for first camera, and these inputs are fed into the RNN sequentially, and the hidden state is the belief state here. But the problem is that in this study, they are trying to select a camera at the end. So when they are actually testing this model in the real world, they don't have all the inputs. So how should they deal with these missing frames here, which we have, which they have shown with dashed lines? One solution is just to avoid updating the states. And authors claim that this method will perform poorly for this task at least, and they are proposing their own architecture, which is called MFRNN. MFRNN updates the hidden state on each time step. It is not avoiding the steps, and it uses an approximated feature for missing frames. So here we have this x hat of t and I, which is an approximated input at time step t for camera I, and those empty inputs are being approximated here. All right. So the usual way that hidden state is updated in a recurrent neural network is that it uses the previous hidden state and the input, and it performs some sort of non-related transformation on it, which is commonly performed by a neural network architecture. And PT is the output of the RNN, which takes in the hidden state and performs again some sort of non-related transformation. And when the input is not given, they are using this x hat of t, which is basically a weighted average of 2 vectors here, xt prime and x null. The weight itself is learned via some sort of exponential function, which takes in delta t u plus v. Delta t is t minus t prime. So t prime, as I mentioned before, is the last time that we had an observation for that recurrent neural network, right? So delta t is the difference, t is the current time step, and delta t is the time difference between those times and time steps. And sorry. Yep. And the weight is being learned via those parameters. So here UV and X null are the parameters that are being learned. And X of T prime is also the last input that the recurrent neural networks observed. So they are using this weighted average of the last observation and some sort of learned parameter here. And how they integrate. So they have multiple RNNs here, how they integrate all these outputs and class predictions. So they have K vectors, each of which are probabilities for for action classes. And delta T of I is T minus T prime for the I camera. So it is the time spent since the RNN has been fed with an actual observation. And to do that, they are averaging over all outputs using a weighted function, which is a function of the delta Ti. And this function itself is an MLP with 2 layers, with K inputs and K outputs. So the intuition behind it is that if it's been a while that a recurrent neural network has seen some sort of actual observation, probably its prediction and its opinion is not that important compared with others. So we hope that this weighted function, this learnable weighted function will cover that. So they can put more emphasis on most recent observations. Right. So as for the policy learning, this view selection policy takes in hidden states from all MFRNNs from all the recurrent neural networks, and it performs actor-critic architecture for policy learning. Each state is represented by all the hidden states and their corresponding delta t's. And reward function is the standard cross entropy, which I believe it is brilliant because it is consistent with the classification part of this network, and also it is always negative. So it is encouraging the reinforcement learning method to to perform this the whole thing as soon as possible, because it is receiving negative results constantly. And discounted reward is GT, which is gamma to the power of t minus 1 times RT. Again, it is a standard way of discounting future rewards. And camera selection policy is denoted as pi of A given ST and theta, in which A is the action, ST is the state of the in time step T, and theta are the parameters of this policy network. And theta is updated by this equation here. Right. Let's go into the results. So we have two kinds of results here. We have trajectory classification and active recognition results. As for the missing frames for the data set NTU, they have two test scenarios in which in one of which, in test scenario 1, we have variable frame rates. It means that some of the frames have been dropped, and in test scenario 2, we don't have that, so we have all the frames. And they are testing the networks for all the viewpoints, and they are adding components to the base network one by one. So the baseline is here, and they added some data augmentation, which improved the performance of the network. And after that, they have input interpolation. Interpolation here refers to performing linear interpolation or linear averaging over frames that the frame is not given. And when it is not given, they are also using the future frames, which is not the case in real life. So I guess it is not really applicable here, but they have reported it, which is good as some sort of baseline here. And they are using MFRNN, which performed better than the previous one, both in scenario 1 and in scenario 2. They also showed the results for IXMath. So we have 5 modalities here. We have data augmentation and MF-LSTM. Instead of RNN, they are now indicating what sort of RNN they actually use. And as you can see here, for most of the inputs, for most of the viewpoints, their model performed better instead for view 3, in which the basic model performed better. But the gap is not that much. And they have also reported the results for the third data set and VGester. In scenario 1, which we have variable frame rates, their model, MF-LSTM plus data augmentation performed the best compared to the base model LSTM and LSTM plus data augmentation. And the same results also holds for test scenario 2, which we have fixed frame rates, which means that the frames are not dropped. Right. As for the view integration, so the network had this view integration parts, and they are trying to show us that this intuition that we are using weighted average instead of the regular average and putting more emphasis on recent observation actually works. So they have this uniform weights, which means just averaging over all probabilities, and they have this learned weight, which was proposed in this network. And we see that in both scenarios, with from being dropped and not being dropped, having this weights learned gives us a boost performance. Gives us a boost in the performance. Right. So let's go to actually the active vision part and view selection. So they are giving us some sort of experiments here for the first data set into you. We have 4 measures: accuracy at 40%, at 100%, and accuracy average. This accuracy at 40% means that the accuracy of that action when only a 40% of the action has been performed. That means if 2 persons are handshaking and if the hands are meeting each other, so 40% before they touch each other, like 40% of the act has been done. So we are predicting it as early as possible. And to be more specific, we are predicting it at 40% of the action. Using all viewpoints is the baseline here, which obviously performs the best, but this is not the point of the paper, and paper is trying not to use all the images at the same time. We have different baselines here. We have some previous state-of-the-arts and other baseline, which is always select view 1, always select view 2, or always select view 3, select random views, and cycle through all views. And at the end, we have the learn policy. And here we see that the learn policy performs the best in all cases, and especially over average, compared with the state-of-the-art and the baselines. The same result also holds for IX math here, which actually the gap between the learn policy and using all views is really small here. It's just 1%. And we have the same results again for NV gesture. All right, so here's a graph they provided for NTU, in which the x-axis represent observation ratio and the y-axis represent recognition accuracy. And the black dashed line is for when the model is using all views at 61.77%. I guess that's average. And the part that we are interested in is using the learn policy here, which is the red line. So one critic that I have for this is that the dashed pink line here is for the case that the model is just cycling through the views. And it is performing really closely to the learn policy, which brings to my mind the question that what is all this hustle about? We have this neural network, we have this policy network that is predicting everything, but actually just cycling through the views is giving out nearly the same performance. So maybe this result is not as satisfying as they initially anticipated. And they also provided some sort of visualization for the policy. Here we have time and we have views, and when we have a dot, it means that the model selected that viewpoint. And looking at these figures, we understand that the policy is not following any sort of trivial trend like cycling through or staying in the same or selecting the same viewpoint over and over again. As for the conclusion, I will cover the contributions made in this paper and also the ambiguities that was in this paper. And also I will provide some questions that might give some sort of ideas for extending their work. So their contributions are threefold. They're proposing, the first one is proposing a well-developed solution for camera selection and early recognition. Second one is development of a novel Cannon network, which was MFRNN, that can estimate the missing values based on the last observation and the elapsed time from that last observation. And third is an approach for integrating information from multiple cameras for view selection and action recognition, which refers to that two-layer MLP, which provided us with the weights. And the key ideas in this paper is using non-uniform sampling rates for boosting the performance and using less computational resources here, using weighted integration for each view's outputs, using non-linear interpolation for missing frames, data augmentation by randomly dropping frames during the training, which led to having two scenarios in our results. Scenario one being without any dropped, with dropped frames, and scenario two being without the frames being dropped. And using reinforcement learning and to be a more specific actor-critic scheme for camera selection. And here's the discussion for this paper. So the first question that I have here is the scalability of this approach. Is it scalable or not? So the best data set that they have was NTU, and it had only 3 viewpoints. Does having more camera points help, and how much camera points do we need? So my answer to this question is having more camera points does not necessarily affect that. So probably this solution is not scalable. Having too many viewpoints will create computational overhead and numerous suboptimal solutions. So I guess it is not scalable. And should RNNs work independently? So this question is important because they're using one RNN per viewpoint, and their idea is that these inputs are not related. And when they are estimating a missing frame, they are also only using the observation from that viewpoint. I guess using a multiple hidden state and using at least the recently observed inputs, hidden state will definitely, will most probably give us a performance boost. And this is a way that people can extend this research. And the last question is, are they considering the latency of performing policy selection, and is it neglectable? So they did not discuss it, and it is important, I guess, because the whole idea behind this paper is to dropping frames and not using all of them because the frames have to be transmitted somewhere else, and this latency creates some sort of bottleneck for early recognition. But the point is that they are using several RNNs here just to select the viewpoint, which has definitely a time delay, and they did not provide the time delay here. So if the time delay is more than just transmitting all the information to the cloud, or in the place that the action recognition is performed, I guess their solution is not justifiable anymore. So this part is also another path that people can extend this research.